Okay, hello everyone. Welcome back to another lecture. I wasn't asked any questions about the last lecture, so I'm assuming it was fine and everyone kind of saw where things were going. Just to make sure, I'm going to do one more curve sketching example. Another very typical type of problem that you'll see in an exam. So we are still using that curve sketching handout that I posted below last lecture. I'll also post another copy to this below, as well as we're going to use another handout today, and I'll post that below as well in the description box or whatever. Okay, so we looked at curve sketching last time. We looked at 6 steps to actually get something sketched using the curve sketching methods, and we spoke about all that good stuff. And now we're going to do more examples. So now we're going to do some examples from the second group of problems. So that is actually going to be an important kind of problem to do. So here, we're given a function. We're also given the first and second derivative, so you don't have to find that. Normally, which isn't weird at all, because usually on a test or some situation where you'd have this, I just touched my face. What am I doing? Normally the situation where my hands are sanitized anyway, so. Normally, on an exam where a problem like this would actually show up, at some point earlier in that exam, we would have already tested your ability to do derivatives, so there's no real reason to test you to do it again. So giving you a function, I'll just give you the derivatives right away when it comes to curve sketching. And yeah, so let's just jump into it. So basically the question here is, consider the function f of x. Boom, f of x equals x squared over x squared minus 4. F prime and f double prime are given and need not be verified. So those are the derivatives, you don't have to verify them or work them out. Find all intercepts, asymptotes, relative extrema, intervals of increasing or decreasing, intervals of concavity, and inflection points provided they exist. Use this information to sketch the graph. Indicate on your graph all the features requested above. So this is a typical problem that you'll see. It'll have those, like what I just said on top. Then you'll be given the function and the 2 derivatives. Let's actually sketch this curve by first going through the motions. Now this didn't specifically ask for a domain. On an exam I might specifically ask you to mention the domain. But that being said, you should know how to actually finish that. Anyway, so this is really, we dealt with this last time, so we're just going to go through the motions here, trying to just make sure that we are, you know how this thing goes, because we did it last week, which was forever ago. So, as I mentioned, the first 6 steps, the first step, even though it wasn't requested here, it's good to know the domain. You want the domain of your function. Now, you know that that factors into x minus 2 times x plus 2. So, plus or minus 2 are bad. So, your domain is all real numbers except 2 and minus 2. So, it would look like that. From negative infinity to infinity, they all work, except at minus 2 it's not going to work, and at 2 it's not going to work. So, we have open intervals here. The second thing we want to find, remember, it's intercepts. So, let's make sure this is recording. Yeah. Intercepts. So, you want the x-intercept, which you know for that you set y equals 0, solve for x. Of course, that means x equals 0. And for y-intercept, you set y equals 0, solve for, set x equals 0, solve for y. Hope I said it the right way the first time. And so that means that your y equals 0, which means the origin is an intercept. Obviously, if x equals 0, the y equals 0 will also be an intercept. Those are the only ones. Plug in y equals 0, solve for x, plug in x equals 0, solve for y. Those give you the intercepts. Nothing strange happening so far there. What's the third thing we should find? Well, hopefully you know by heart by now that asymptotes is the next thing. So we are going to find the vertical and the horizontal asymptotes. Let's start with vertical asymptotes. For no reason. So remember, the vertical asymptotes occur when the denominator is 0 and the numerator cannot be 0 at the same time for a rational function. So there's nothing to cancel the 0 factor in the denominator. So x equals 2 and x equals minus 2 are vertical asymptotes. Horizontal asymptotes. How do we find horizontal asymptotes? That's right, you find the infinite limits, or limits at infinity, to be technically correct. So we're going to want to find the limit as x approaches infinity of our function. Now, it's a rational function, so whether you approach positive infinity or negative infinity, you're going to get the same idea. Technically speaking, you should check both, even though in this class, the only kind of functions I'll ask you about will be the ones where both sides will actually give you the same thing. So, as x approaches infinity, what does that approach? Now, hopefully you said 1, because that's the answer. So y equals 1 is a horizontal asymptote. Right? So this is just the ratio of leading coefficients idea. The highest bar is the same in the top and bottom. So the limit at infinity goes to the ratio of the leading coefficients. So it's the 1 divided by the 1. Okay? So far so good. Next we want to do the intervals of increasing, decreasing, and the maxes and mins, which basically means the next step is the first derivative test. So we want increasing, decreasing, max, mins. What tells us about that? Now, hopefully you told me that the first derivative tells us about that. Now, the first derivative was given, I believe it was minus x over x squared minus 4 all squared. And yep, that was it, minus 8x over x squared minus 4 all squared. So we want to set that equal to 0 or undefined. Now, of course it's equal to 0 if your x is equal to 0. It's undefined if your x equals plus or minus 2. These are your critical points. So what we do with the critical points is we plot them on the number line. And we plug in random numbers in between them in the first derivative. So I can try a minus 1, plus 1, 3, a minus 3. I'm going to plug that into the first derivative. Now, one thing I want you to notice about the first derivative here, which is not something that will work in general, but for this particular function, it's nice. Notice that the denominator is a square. So as long as I'm not at plus or minus 2, the denominator is going to be a positive number. It's going to be greater than 0, which means the sign is going to be affected by the numerator. So once I figure out the denominator is always going to divide by a positive thing, so I just know whatever I get divided by a positive sign, it's going to give me the sign of the whole thing. So just focusing on the top, minus 8x. If I plug in minus 3 into there, I would get a positive number. If I plug in minus 1 into there, I would get a positive number. If I plug in 1 into there, I would get a negative number. If I plug in 3 into there, I would get a negative number. So this means positive in the first derivative means, that's right, it means increasing. Negative means decreasing. Now we're going to try to identify maximums and minimums. Now these two guys are not in the domain. They're not a maximum or minimum anyway. However, 0, you're increasing on the left, decreasing on the right. That boy is a maximum. Which, by the way, now we can actually write down a part of the answer. So we are increasing from negative infinity to minus 2, union minus 2 to infinity. We are decreasing, minus 2 to 0. We are decreasing 0 to 2, union 2 to infinity. We have a maximum, maximum occurs at 0, 0. Minimum, we have none. So that is one of the answers we have here. That's us writing the first derivative test. And in fact, let me copy this information down because we are going to need it at some point. So increasing minus infinity, minus 2, union minus 2 to 0, decreasing 0 to 2, 2 to infinity, and we have a max at the origin. Okay. All this information is going to be useful later. Right? And we had vertical asymptotes. I should be writing that down as well. Vertical asymptotes, well, that's at x equals 2 and minus 2. Horizontal asymptotes, that's at y equals 1. The intercepts are just the origin. Okay. So now we move on to step 5. Now in step 5, you might recall, we figure out where it's concave up, concave down, and if there are any inflection points. So now, what do we need to tell us about that? Well, yes, we need the second derivative. So we're given the second derivative. It is f double prime equals 8, 3x squared plus 4, x squared minus 4, cubed. Now, of course, you need to find the critical points here, so you set this equal to 0 or undefined. If it's equal to 0, that means 8 times 3x squared plus 4 equal to 0. There's no solution here. Never 0. Right? Because you have 3x squared plus 4 is never going to be 0. It's always going to be positive. It will always be at least 4, by the way. It is undefined, well, for the same plus or minus 2. So those are your critical points. So we are going to draw this line. We're going to put in minus 2 and 2. Those are the only critical points. We are testing this in the second derivative. So I am going to plug in some random numbers like 0, minus 3, positive 3. Now we can notice almost a similar idea here. Notice that the numerator is always going to be positive. So I only have to worry about the denominator, right? And then this thing is cubed, so it'll take the sign of whatever's inside. So if I plug in minus 3 into x, I would get 9 minus 4, that's positive. Cube it becomes positive, and then on top you have a positive number, so it's all positive. If I plug in 0, I get minus 4. Minus 4 cubed is, of course, negative. On top it's positive, so it's positive divided by negative, it's negative. Then if I plug in 3 into that, the top is positive, the bottom is 9 minus 4, which is also positive, so it is positive. So, what does positive mean in the second derivative? That's right, it means concave up like a cup. Same thing here, up like a cup. Negative means down like a frown, concave down like a frown. You're negative, you're feeling sad. Okay? Now, remember, inflection points are where we switch concavity. So, what are the inflection points here? If you said minus 2 and plus 2, you're wrong, because minus 2 and plus 2 are not in the domain. So, while they are from this test, they look like candidates for places where they are candidates for places where inflections would occur. We know for a fact that they do not occur there because the graph does not exist here. So there are no inflection points. There's no place where you switch concavity and at the same time that coordinate is actually on the graph. So no inflection points. However, we do like to summarize here. So we will say we're concave up on the interval minus infinity to minus 2, union 2 to infinity. we are concave down on -2 to 2. Inflections, there are none. And that is a part of our answer. We boxed this because it was specifically requested in the problem. Let me copy this information down, that's going to be important later. So concave up on -infinity to -2, union 2 to infinity, or concave down on -2 to 2. No inflection. Okay? This brings us to step 6. So we found everything that the question asked us to find. Now it comes down to actually using this information to sketch the graph. So what we're going to do is we're going to draw axes. We're going to put all this data that we have on the graph. Then we're going to forget about the data and draw a picture that obeys all the requirements. So let's make that the y-axis. Let's make this the x-axis. And let's throw in those guys. So remember, the first thing we kind of want to do is to find, plug in the points, the actual coordinates that are important. We had one that was important. It was this point here, which was the x and y intercept. It was also a maximum point. And I believe that's the only actual coordinate that was important here. We didn't find any other intercept, so that's the intercept. It's also the maximum point. There was no inflection point. There's no other point we need to pay attention to. So the next thing we want to do is put in the asymptotes. So we have the vertical and horizontal asymptotes. Where's my... So let's, for vertical asymptotes, let's use, right? So we have that, and so at 2 and -2, we have vertical asymptotes. I mean, do I want to let's make this a little narrower. It's not drawn to scale, so that's at 2. When things are so big, it's hard to. That looks a little better. That's at -2. So those are the vertical asymptotes. Horizontal asymptote, I believe, was at y equals 1. So let's go here. That's at y equals 1. And now, what we also want to do is we want to put in the intervals. So the intervals of increasing, decreasing. So where are we? So intervals of increase was from -infinity to -2. So from here going back, we're increasing all the way from -2 to 0. So from here to there, we're increasing. We are decreasing from 0 to 2. That's decreasing here. We're also decreasing from 2 to infinity. So decreasing there. Concave up. We're concave up from -infinity to -2. So from here all the way back, we are CU. And from 2 to infinity. So from here all the way forward, we are CU. And we are CD, concave down, in between CD. And now all the information that we calculated before is on that picture. So this is what the skeleton for your graph should look like. And now we're just going to draw a graph that fulfills all these properties. So of course, if this is a maximum point, you're expected to be increasing towards it, decreasing towards that. And it tells you here, like in this entire middle region, you are concave down, down like a frown, which means you shape like a frowny face. You hit a maximum here, which means you're increasing up towards that maximum and then decreasing afterward. And this is a vertical asymptote, so you can't touch that line, so your graph looks like this. So f of x is the yellow line. Now, you would go above here. You want to talk about this region. Now, we know there's no intercept, so we never actually touch that, which means I can't decrease like this. Or in fact, I can be below here, because if I'm decreasing the whole time, eventually I would have crossed that. Now, I can't be above here either. One way you can see that is that if you're decreasing, you'd look like this. But if you did that, you would have to actually settle here, because that's the horizontal asymptote. And that would create another minimum point, and we know there's no minimum point. Which means we have to also stay above the blue line. So we have this. So we never actually touch the horizontal asymptote, we're always above it. So that's the graph there. For similar reasons, the graph on this side would look like that. Now, you kind of know that it won't, you know that it doesn't touch this because it has to be decreasing the whole time and it would have to increase to come back. Another way you can know that it doesn't touch the horizontal asymptote, because it's possible in general to touch the horizontal asymptote, you can actually try to solve for where it would hit the horizontal asymptote. So this is where y equals 1. So you might want to ask the question, does f of x equals 1 anywhere? Well, that would mean that x squared over x squared minus 4 equals 1. But that would mean that x squared is equal to x squared minus 4 if I multiply both sides by the denominator over here. And I can subtract x squared from both sides to get 0 equals minus 4, which of course doesn't make any sense. That's ridiculous. And so no solution here. So we know that f of x never actually hits 1. So the y value is never actually 1. It will never touch that line. Because we know it would never touch that line, it can't start below it because it has to be increasing. If it starts below and increases, it'll hit it. So you have to always be above that line. So there are a couple ways you can figure out that the graph, which is the yellow line, has to be above the horizontal asymptote the whole time. And so that's what your graph looks like, that yellow line there. So this is our graph. It goes like this, with a maximum in the middle. That's the final curve sketching example. So hopefully that wasn't so bad. Hopefully it connects a lot of things more streamlined that were brought up in the last lecture. And I would say, of course, that you should practice by doing the other two problems in this section. There, here, and here, which I will post below. But for now, that was just to kind of connect last week's lecture to today's lecture. But what we're going to do now is jump to a completely different topic. It's one of the last topics in this section of the class because we're kind of wrapping up all the things I wanted to talk about with that concern derivatives, and we kind of want to talk about some other things, the other side of calculus. But yeah. One of the last main topics, I'm pretty sure this is actually going to be the last thing that's directly only uses the derivative only. And that topic is Drum roll. Well, if some of you are paying attention to the syllabus, you know it's optimization. So this is another application of derivatives. We just finished an application that it applied to curve sketching, which, as I mentioned, other than in a calculus class, no one's going to sketch a curve by hand. It's really only there to test whether you know what the different derivatives actually do and gives a visual representation of your understanding as to what they do. Optimization, though, this is something that is used in real life. I don't know if any of you are ever going to use it in your real life, but optimization is a very, very important thing. And one of the ways in which we can do optimization, there are many, but calculus provides one way to do it. And the derivative is indispensable in the calculus way of dealing with optimization. Now, as I mentioned a little bit earlier, there is a handout that goes with optimization. It's this guy right here. Optimization. So I explained a little bit about what optimization is here. It goes again into some steps on how to solve optimization problems, which is 6 steps once again. Pretty much every time I give a handout with a bunch of steps to do something, it's always 6 steps. It was a coincidence, I promise. But yeah, a lot of these things, related rates had 6 steps to it, curve sketching had 6 steps to it, optimization now has 6 steps. So it's one of the last things what we'll be doing. There are 3 pages in this document. Gonna do a few examples jumping around. I'm not actually sure if I'll do this example, but I might. There's an example over here. We'll see how I feel. I'll definitely won't do that today's class though, but I might do this example as an extra optimization example in the next class before moving on to something entirely different. Now, a lot of our problems are going to look like this. So again, these are word problems. So there is a potential for you to get mixed up as to when to apply what. So I'm going to talk about pretty much how you would know that you're looking at an optimization problem. So optimization basically means it's a method of optimizing something. So to optimize something means to make it as good as it can be, which I know sounds a little bit vague, but there are many situations in which optimizing something really boils down to maximizing or minimizing it. Often, this boils down to maximizing or minimizing something within constraints. Now, once you see maximizing and minimizing, you're going to think, oh wait, derivatives help us with that. Derivatives help us maximize and minimize things within constraints. So, for example, you are running a business. You have a function where it's measuring your profit. You want to know how to maximize profit. To optimize the profit situation, in your mind would be to maximize profit. Or maybe you have a cost function that you're measuring. It would be in your interest to minimize your cost, minimize the cost function. Or maybe you are building a product, but you know, you're all about save the whales and save the environment and stuff like that, and so you want to use the least amount of materials as possible so you have the smallest footprint as possible. What you then want to do in your mind to optimize the situation means figure out a way to use the minimum amount of materials. So I have to displace the minimum amount of environmental material, etc. Right? So a lot of times optimize, to make something as good as possible, to make something the best it can possibly be, means just make it bigger, as big as it can possibly be, or make it as small as it can possibly be. No, as good as it can be is because in real life, making something the biggest and the best is not always possible, and minimizing something to the point where it becomes zero isn't always possible. You will always have constraints. There will always be constraints. So a constraint is a restriction, something that stops you from making something infinitely big or zero small, right? So if you are someone, like I said, concerned about their profits, you want to maximize profits, well, there's only so many hours in the day, you can only hire so many people, you can only rent so many space, you can only buy so much equipment to make many products. You get the idea. Like, you can't say, oh, I'm selling hot dogs, I'm going to sell an infinite number of hot dogs so I can make an infinite amount of money. Like, it's not going to work. There are constraints. You can't make an infinite amount of hot dogs. There's a finite amount of hot dogs you can make, and you can directly figure out by yourself, or whether you hire employees and have all of them made hot dogs. There's only a certain amount of hot dogs that they can make to make a maximum profit. So there's always going to be a constraint. There will always be restrictions. In life, you never have infinite resources. You have a finite amount of resources, and you want to get things to be as good as they can possibly be, given that you have to abide by all these restrictions that you have. These restrictions are called constraints. So overall, the gist of it, that's what optimization comes down to. You want to make something as good as it can possibly be within certain constraints. And oftentimes, that amounts to maximizing or minimizing something when you have these constraints. Now, how do I actually turn this mathematical? And by the way, just by me describing this kind of tells you when you're looking at an optimization problem, right? So you're going to be told about some situation, and you're going to be told in some way how you want to make it as good as it can possibly be. You're also going to be given some restrictions, and I'm going to tell you how to know when you're given a restriction versus when you're just being told about something else. But that's the gist of optimization. Once you realize you're in an optimization situation, so someone says, oh, we want to maximize this, we want to minimize this, we want to make this as large as possible, we want to make that as small as possible. This is the situation we're in, so we have this restriction. So you recognize it's an optimization problem. Once you recognize it's an optimization problem, you're going to go through these 6 steps to solve an optimization problem. Now, when it comes to optimization, the process is a little bit more complicated than, say, the process for related rates would be. So I like to talk about the steps while going through an example. So what I'm going to do is I'm going to go through the first example in the handout, and as I'm going through those examples, I'll explain to you the steps that I'm taking in going through those examples. And by the way, again, I wrote down the steps, and as you can see here, I fully flesh out what you should be thinking about when you're going through the steps, but I also wrote in bold like the things that you're supposed to think about, like on a test basis, right? So you really want to fully read this a few times, but once you think you had it internalized, just remembering the bullet points should kind of jog your memory as to what you'd want to be able, what you'd have to do to get through the problems. So I talk about the 6 steps here, and I also explain, kind of elaborate on what it would mean for you to apply them, why it's important for you to apply them, etc. Read the handout, very important. I will drop it in a link to it in the description. Okay. So we're going to do, on the second page, example 1. So hopefully you pulled that up from the link, and you can read with me. Because, as it turns out, step 1 is to read. Just like with related rates. Read the problem. Carefully. Read the problem. So step 1, read. Read carefully. So one, you need to read so you can figure out it's an optimization problem, but two, it's way too late. Two, you should read the problem carefully so that you can pick out the right information and apply it in the right situations, which I will discuss with you at length. So, problem one, a farmer has 100 feet of fencing. He wishes to make a rectangular enclosure. So he has some fence, wants to build a rectangular enclosure. If he wants to enclose the maximum possible area so he can plant the maximum number of crops, what should the dimensions of the enclosure be? So here's the situation, just so that you have a visual, kind of fully understand it. You have a guy who has a fence, he wants to build a rectangular fence, right? So you can imagine this is the bird's eye view of the fencing. He has 100 feet of fencing. Which means the perimeter of this must be 100. Now, one thing you should be able to appreciate is that there are a multitude of ways that he could build this rectangular fence. He could do 40 feet, which adds up to 80 feet, then 10 and 10. So that's 100 feet going around, and that's a rectangle. He could also have 30, 20. He could have 25. He could have 45, 5 and 5. Like, there are so many ways that you could make a rectangle where the perimeter is 100, but he wants to find the best way. And what does best mean in his mind? Maximum area. Give me the maximum amount of space so I can plant the maximum amount of crops. Now you'll notice here, like the area here is 400, while the area here is 600. So yes, the perimeter is the same, but the areas are actually different. This one has a bigger area than that one, right? And so on and so forth. So you can have many examples of how to build a rectangle with 100 feet as the perimeter, but the areas will be different between each example. You need to find the one that has the biggest area. That is optimization. So, what is the constraint here? Well, the amount of fencing he has. He doesn't have an infinite length of fence to build the biggest possible rectangle, right? So, he only has 100 feet of fencing. So that's the constraint. And in fact, in general, that's how you can identify the constraint in an optimization problem. What you're going to do is you're going to look for the thing where a specific value is given, where they say, you only have this much stuff. There's only this much thing. Specifically, here's a constant. That's how much stuff you have. That is automatically your constraint. So here, we hopefully understand the situation. Guy wants to build a rectangular fence. He only has 100 feet of fencing to do it. How can he do it in the best possible way? Where best here is defined, it has the maximum area, maximizing something. So we read, so we understand the problem. The next thing we want to do is to draw a diagram. Draw and label a diagram. So much like in related rates, we want to draw a diagram of the situation. In this case, of course, the diagram is a rectangle. So now, here's the thing though. How would you label this? As I mentioned, there was a multitude of rectangles. You can make the length and width anything you want. So, the length and the width are yet unknown. So, I would just label both of them with variables. So, I can call this length x, that length y. That's my diagram for the situation. So, I'm going to read the problem, fully understand its optimization, fully understand the situation. I'm going to draw a diagram that represents the situation accurately. I'm going to label that diagram. So now, ultimately our goal is find the length and width, find the x and y such that the area is as big as it can possibly be. This brings us to the third step. Now in the third step is where we set up our constraint and objective equations. maybe I'll write this slowly. So in related rates, we only set up one equation. Here, you actually need to set up two equations. You need to set up the objective equation and the constraint equation. And these two equations actually try to look at different things. Now, the constraint equation, what that does is describes the given restriction or constraint. Right? So again, there's going to be a value that you're given, right? You're going to be told this is how much stuff we have to get this thing done. Write an equation that describes that in terms of the variables that you put in your diagram. That will give you the constraint equation. Now the objective equation, this describes the thing you want to maximize or minimize. That's your objective. Your objective is to make this thing big or small. Describes quantity you want to optimize. Now, you think about, well, in reading this problem, what was I told was a constraint? The very first sentence tells you the constraint. The farmer had 100 feet of fencing. So, pretty much the length around the fence is the restriction. So in this case here, perimeter is your constraint. And we actually know an equation for perimeter. So that basically means 2x plus 2y is the constraint. And we're told that that constraint is 100. And in fact, we can simplify this. There's 50. It's not the final answer, but that's your constraint equation. So constraint equation describes the thing that constrains you, the restriction that he has. And in this case, the perimeter was the restriction. He only has 100 feet of fencing. So I wrote down the equation in terms of the variables I have. Now, what is it you want to optimize? Here, what you want to maximize specifically is area. So now you just want to write down an equation that gives you the area of a rectangle that has length x and width y. So here, we don't know the area, so that's an unknown. I'm going to write A for area. How can I find the area of this rectangle? Well, it's x times y, length times width. So notice in your objective equation, everyone's a variable. You would have 3 variables usually. And that's your objective. It describes the thing you want to maximize or minimize. So for this kind of problem, you actually need 2 dos equations. A constraint equation and an objective equation. Now, hopefully, why those, in this case, these 2 are the equations we need, hopefully that is clear. But if not, just drop a question down below or email me. So, those are the 2 equations. Now, step 4. You're going to create a new equation. In fact, it's going to be a new objective equation. And you always create this the same way. You're going to solve for a variable in constraint and plug it into the objective. Now the goal of doing this is to get your objective equation in one variable. Here I have a function that describes the area, but there are 2 variables, and this isn't Calc 3. We don't know how to differentiate things with multiple variables. At least, yes, we do have implicit differentiation, but there is no third parameter that we know of where we know the rates of change. So having 2 variables here where we don't know about their individual derivatives is kind of tricky to deal with at calculus 1 level. So what we want to do is get this into a single variable function. Actually just solve for one variable here and plug it into there. It's always what you're going to do. You're going to take the constraint equation, solve for somebody, you're going to plug it into the objective equation. Right? So, since, and in general you can solve for anybody, but let's just here solve for y. Since y equals 50 minus x, this means that a equals x times 50 minus x. That is, your a is equal to 50x minus x squared. That is your new objective function. So notice now you have the area written as a single variable function. In fact, it is a quadratic. Now I'll give you some time to copy this now. We're not done, but I'm going to need to create some board space here pretty soon. So I'll give you some time to copy that down. Pause in 3, 2, 1. Pause! Copy. Now hopefully you got all that. Alright, so now what we're going to do is we're going to move on to step 5. Now that we have the objective in a single equation, you're going to find the, now technically you want to find the absolute max or the absolute min as is required, which means you should technically be testing endpoints like in the closed interval method. But in this class, the endpoints are rarely going to be the answer, so, but it should be something that you think about. So you're going to find the absolute max or min of the equation in for, say, new objective. This is where you actually start to optimize. Here's where you want to make this thing, which is the area, as big as it can possibly be, or as small as it can possibly be. Now, technically speaking, for this particular example, we don't need calculus. That's a parabola, and we actually know how to find the maximum point of a parabola that has a maximum. You should be aware that this is an inverted parabola, which means the maximum occurs at the vertex, so you should be able to actually find that without calculus. However, sometimes you're going to need calculus, and so I'm going to show you the calculus way to actually complete the problem. So, how do you go about finding a max or a min? What do you need to do? What's the first thing you want to do when you want to find a max or min? That's right, you find critical points. So, first thing you're going to do, you're going to find the derivative. Now, of course, this is a as a function of x. So I'm going to differentiate with respect to x. This will give me 50 minus 2x. And so you set a prime equals 0 or undefined for critical points. Now this is never undefined, it's a polynomial. This means that you need 50 minus 2x to be 0. This means x equals 25. Now, in general, when you get one answer, chances are that's the answer you want. But there are times when you can get to this situation, and depending on the equation that you have, it can have several critical points. So it's always good to actually just check. So you check here. Now, what are all the possible x values that you can have? Well, he has up to 100 feet of fencing to actually use, and he could actually, in theory, give a 0 amount of fencing to the width. But of course, here's what I mean about when you're finding absolute max or min. The extreme points, Usually in a real life situation, they're not going to be the answer because they're going to be an extreme situation where there is no answer. Notice that if I put 100 feet on the x side, there will be 0 feet on the y side, and hence we will have no rectangle. Also, if I put 0 feet on the x side and 100 feet on the y side, that's another extreme example. We don't have a rectangle. So the endpoints are not going to be the answer, even though finding the absolute max or min, technically you'd want to consider the endpoints. But the endpoints would give you an area of 0, so they are not the answer. So we're looking for a local max or min, which is very usually going to be the case, and we know that there's a critical point around 25. So what I can do is I can plug in 26 or anything larger than 25, between 25 and 100 into the derivative. I can plug in, say, 1, which is on the left side of 25. Now if I plug in 1 into this, I get 50 minus 2. That is positive, which means increasing. And if I plug in, that is positive, which means increasing. And if I plug in 26 here, 50 minus 2 times 26 is minus 2, so that is decreasing. So I'm increasing, then I'm decreasing, which means 25 is what I wanted. It's a maximum. But normally, like I said, when you have one critical point, normally testing it doesn't even make any sense because that's going to be the answer, right? It's the only candidate. But here, it actually works out that it is a maximum. And so, yeah, we need x equals the maximum. X equals 25 for the maximum. You need 25 feet on the x side. So this leads us to problem 6, which, just like related rates, the first step was read, the last step is to answer the question. So you are going to be asked for something specific. So the problem might have asked, well, if the farmer wants to build a fence, what is the maximum area? In which case, you can just take x equals 25, plug it in here, that's your maximum area. However, in this case, I believe the question is, what should the dimensions be? Which means you need to tell me what is the length and the width. Now, so far we know the length, so we need to find the width. So here we want dimensions. So x equals 25, and I know that my y is 50 minus x from here. This means that your y is 50 minus 25, which is 25. This means your dimensions, it's a 25 by 25 foot enclosure. Or you can say x equals 25 and y equals 25, or you could say the length is 25 feet and the width is 25 feet. But either way, you can finally answer the question. And that, ladies and gentlemen, is a fully worked out optimization problem. Now let me give you some time to copy that down. And step 5 and 6 here, this I don't want you to think is the last step. Okay. And that is optimization, which I think we're pretty much out of time. Time's been flying fast, but I've recorded a bunch of classes today and I think I'm just moving a little bit slower. Too tired, it's late. But yeah, that example kind of tells you how this thing is going to be done. So next time I think I'll just spend it doing more optimization examples, just getting used to it, including the last one. And then the class after that, I think I'll move on to a completely different topic. Yeah. But in the meantime, what I would suggest is you get this handout, which you can find at the link below. It's also on your class webpage, which is what I linked to below, actually. The link directly that takes you directly to the PDF of this, but there's also a link on your class webpage. And so what I would say is actually try some of these. So for next time, which it's probably good that you try these today so that you can ask me questions if you miss something. So I can deal with those in a Q&A in tomorrow's class. So try for next time. Problems 2, 3, 4, and 5. I think next class what I would do is I'd probably do 2 and 5. Maybe 4 also. Might throw something like 3 on a quiz or a test or something. And the last page, like I said, that's something that, it's optimization, but it's applied in a very specific way to inventory costs. I'll probably deal with that tomorrow as well. So I'll probably go through these examples, maybe do an inventory cost example. And with that, we should be finished with the applications of derivatives. I don't think I'm going to do anything else after that, but we're going to move on to something completely different after that. But yeah, that's that. That is optimization. Hopefully everything was fine, but if anything I said sounded like gibberish, which is entirely possible, just leave your questions, and yeah, have a good one. Stay safe, stay home, but keep studying, keep working hard, because this thing will end eventually, and you'll have to go back to the real world, and you'd have to actually show something for all the time and effort that you're putting into the class. Still no word on testing protocols. I've been asking, and like I said, I already know what I want to do, but I can't really do it without things being sanctioned, and that would come from the math department, and the math department wants permission from the deans to actually implement something. So there's like a whole chain of command that we have to go through. So sorry for the delay there, but like I said, as soon as I figure out something, I will let you guys know. Our next test should be around the end of April, so we do have some time. But I'd like to give you a testing protocol way before then, so hopefully something comes through. If it does, I will be for sure to let you know. Until then, take care, have a good night, try these problems for next time, watch the lecture and ask me any questions. Be sure to timestamp them, and I guess that's it. Ciao.